We don't all need to have followed every intricate detail at the recent COP26 climate conference to know that radical action is required to stay on target for global greenhouse gas emissions. We see targeted improvements aimed at almost every carbon emitting sector, and heavy industries, which is responsible for nearly 40% of global greenhouse gas emissions, is by no means an exception. Knowledge is power in this fight on climate change. It allows for sensible, timely, and financial decisions to be made, ultimately guiding us towards our climate goals. TransitionZero is a climate-oriented company, and with my project, we take a deep dive into the heavy industry sector and look to combine satellite imagery, facility metadata, and machine learning to extract accurate facility-level emissions data in near real time. So what do we mean by facility level, and why is this important? In many countries, heavy industries export data is publicly available and already useful in national and international policy making. Any given country, however, will consist of many facilities, of which specific information about emissions is not known. Identifying information at this level will promote more targeted insights into the economic vulnerability of particular plants and parent companies. So with this in mind, we can outline the aim of the project, which is to predict accurate facility level emissions in both the steel and cement industries. Our approach to do this, however, is not so direct. We've first got to look at liquefied natural gas, which has the facility level data. We develop a generalizable methodology. We can then validate this performance on the facility level data and then apply it back to these other sectors. So what sort of features are we working with? At this point, I'll introduce the feature extraction process. With this methodology, features are identified based upon the amount of radiation that is emitted under the hypothesis that it will capture the most fundamental processes in manufacturing. We begin with a set of facility coordinates, and we're able to extract this radiation data on an approximately weekly time frame. This data, which often contains a certain amount of noise, then undergoes a pre-processing stage. This is what it looks like following pre-processing. We can see that the significant groups of hotspots are now formed together as individual features, and certain noise features such as the gas flare and water interference signals are now removed. So what does our overall data set look like? Well, first off, we look at one country, the USA, and we look at 3 particular LNG facilities. In total, we have 15 features, and in total, we have 65 training samples and 13 testing samples. So following on from our aim, we must identify something now that shows how this task differs from other more standard machine learning approaches. In a standard machine learning approach, you'll get a set of features, i.e. in this case, facility hotspots, and train it on a set of target data, i.e. country level exports. What you typically expect is to use this model to now predict country level export data. However, in our case, we're wanting to use this same model to infer the desired model output prediction, which is the facility level export data. So how do we go about this approach? Well, a rigorous modeling methodology was used in order to fully explore the solution space. We begin with model selection. We then apply certain feature reductions, feature transforms, cross-validation process, and hyperparameter tuning. And from this extensive process, we identified the optimal solution. So this solution involved a custom SciPy function, which I implemented into sklearn, and this introduces facility level capacity data into a regression equation. We apply a principal component analysis to reduce the number of features to 1 per facility, a min-max transform, and ultimately a logic sigmoid function to smooth extreme values. This overcame one of the major limitations of the standard regression model, which was the high correlation between facilities. So when we compare our custom function to a baseline linear model, both we can compare both at the country level and at the facility level. So on the y-axis, we have performance, where 1 is a perfect score. And on the x-axis, we have rates of production. So we can see for the total country level exports that the difference between custom function and baseline function is basically nothing. However, when we look at an individual facility, we see that the custom function far outperforms the baseline function in almost every region of production. So in conclusion, we have an effective modelling approach, which is now validated for the LNG sector. For future work, we can look to address additional sectors within heavy industries which do not have the benefit of validation data. We primarily look at iron and steel and cement, which have a total CO2 emissions of about 15% globally. Thank you.